Now, when we count a swinging pendulum, if we change the length of the pendulum, the time it takes to swing is going to change. If we graph the time between counts, so let's say we're counting 1, 2, 3, 4, 5, 6, 7, 8. If we graph the time between counts versus the length of the pendulum, then we're going to test this to see if we have a constant ratio of y values when the x value doubles. That is, when the length, which is the x value, doubles, do we always have the same ratio of the times between the counts? Now let's see what that means. Let's say we get a graph that looks like this. Okay? Now, x between here and here doubles because x is this big and then x is this big. And this distance and this distance aren't exactly the same because I didn't draw it really well, but they're intended to be the same. And for the purposes of illustration, let's assume that these are the same. What happens to our y values? Well, we could put a little notation in here. We could call this value x1 and this value x2, and then we could call the corresponding y values y1 and y2. Now, y1 represents this much on the y-axis. So this arrow here represents the value of y1, and this arrow represents the value of y2. If we had a tripling graph, in other words, if y triples when x doubles, of course we know that graph goes up like this, but y2 would have to then be 3 times as high as y1. And that's clearly not the case. y2 is not even twice as high as y1, but it is higher than y1. So that the ratio of y2 to y1 is not 3, as it would be in a tripling graph. You know, y triples when x doubles. It's not even 2, as it would be on a straight line graph, but it's still something other than 2 or 1. So that we want to know by what factor y changes between this value and this value. That is, how does the time between counts change as x doubles? Okay, well, in this case, it looks like y2 is maybe 1 1/3 times y1, maybe 1.3. Let's test that. Now, if this is 1/3 of this, well, let's see. Then that would mean that y2 is 1.33 times y1. Okay, this distance here, if we go 1, 2, 3 times, it's too far. So I'm thinking that y2 is probably about 1.4 times as big as y1, and you should be able to reconcile that. Which means that this, which represents y2, and I can put y2 here, is about 1.4 times as big as y1. Okay, now, this is a power function if that ratio is always the same. So let's kind of check out and see if that's the case. Let's go ahead and get another pair of x values, okay? And let's just take this value and this value, okay? So here, again, the x value doubles between here and here. Now what happens to the y value? Well, of course, I'm doing this freehand, and it's not going to be really great. But the y value, of course, the second y value would be this one, and the first y value would be this one. So we would be comparing, and let me think about how to draw that. I'm going to pause for a second. We would be comparing this value here, and let me just draw this as an arrow. Okay, the length of this arrow, it's a double arrow, and that's probably inappropriate, but let's not worry about it right now, to this arrow. Okay, so as x doubles, again, y gets bigger. Does it get 1.4 times as big? Well, this distance here is more than half of this, which means that this is more than 1.5 times as big as this one. So that let me write that down as a statement. I'll do that off screen so you don't have to watch me write it. Okay, we see then that this is a little more than 1.5 times this, again because this difference here is more than half as great as this. So I'm going to say this is about 1.6 times as big as this. Now, our conclusion there is, and of course x doubles between here and here, that here x doubles and we get y increasing by a factor of 1.6, whereas when we double here, y increases by a factor of about 1.4. So that doesn't satisfy the criterion of this family of functions. So if we had this observation, if this was the accurate curve, we would conclude that this is not a power function. Now let me write a note and clarify what I mean. Okay, my statement is that the y ratio is not always the same when x doubles, because here we have a doubling of x and a ratio of 1.4, and here we have a doubling of x and a apparent ratio of 1.6. If that holds up, if we do the graph accurately, and that really is the way it works, then this isn't a power function. Now, we haven't defined what a power function is. I'm simply saying a power function is one where the y ratio is always the same when x doubles. So y ratio is always the same when x doubles. That means we would have a power function, as we very likely have down here. Now, here's another set of data. I've drawn another graph, and I've used the numbers from one of the students that did this today. And where we have lengths of 1/4, 1/2, and 1, we got y values of 0.4 seconds between counts, 0.53 seconds between counts, and 0.7 seconds between counts. Now, between length 1/4 and 1/2, the x value has doubled, and the y value has increased from 0.4 to 0.53. That's an increase of the factor of that increase is 0.53 over 0.4, which is 1.35. If we go from 1/2 length to length 1, then we have another doubling of the length, and the y value, the time between counts, went from 0.53 seconds to 0.7 seconds. If we divide this by this, we get 1.32. Divide this by this, we have 1.325. So we're going to conclude that when x doubles, y increases by a factor of 1.32. Now, to reinforce that, I've added a brief note here. That 0.53 over 0.4 is 1.325, 0.7 over 0.53 is about 1.32. Those numbers are very close. And this is very consistent with the idea that when x doubles, y increases by a factor of about 1.32. So this does appear to be what we call a power function. Now, again, I haven't defined a power function, except that a power function is one where the y ratio is always the same whenever x doubles. Now, there's a little more here and here, and I'm going to stop this video at the time and right now and talk a little bit about these things, which go a little beyond what we're actually expecting everybody to be able to do at this point.